This instructional video gives a description of how to use real space modeling to predict what scattering you might see from a variety of shapes or structures that are not necessarily the simple geometrical shapes where there are analytical functions or numerical integration is possible. To get started, from the Macros menu, choose Load Real Space Modeling. This loads in the normal analysis functions, as well as loads in, barely off screen, the Real Space Modeling panel. These two windows are extraneous. We don't need these right now. From this FFT panel, or Real Space panel, it allows you to set up a volume in real space and then fill that volume in real space with cells of some scattering length density, forming an object, and then taking that object in real space and using one of several different methods, calculate the scattering from that object. The scattering from that object can be calculated either in one-dimensional I versus Q, or by using a fast Fourier transform, you can calculate the two-dimensional projection of what you would see on the detector based on the orientation of that particular object. What you set up on the panel is the number of cells per edge. In this case, you will be working with a box that's 128 by 128 by 128, and in real space, the length of each of these cells would be 5 angstroms. That limits the total size of the object that you can calculate. An approximate Fourier transform time of 2 seconds for this, just to give you an idea of how long the calculation might take. Your Q maximum of about 0.6 inverse angstroms, and a delta Q spacing, which is close to what your minimum Q for this configuration would be, of about 0.005 inverse angstroms. So for this configuration, depending on the size of the object, you may want to make a larger box, which means a larger calculation time, or a larger length per cell, which allows you to create larger objects much easier. If we click Make Matrix, this builds this matrix, and additionally, if you have already used this, you can save the matrix with whatever object you've created, reload it in, or you can create two different matrices with different objects in them and add them together. This can be useful to create more complex structures much more easily. Solvent matrix means to fill the matrix with a solvent. Currently the matrix is filled with zeros, and the units of this are 10 to the minus 7 inverse angstrom squared. So if you wanted something that was, say, D2O as a solvent, you would enter 63 and then fill the solvent matrix. Keep in mind that scattering length density is all relative, so for simple calculations, you can simply leave this 0. Generally, you work top down from the panel. Make gizmo is the next step. This will draw off screen a three-dimensional representation of the matrix. Currently there's nothing in it, and you can just see the X, Y, and Z axes. In this representation, in fact, due to the way that Igor labels the axes, the beam is incident in the negative X direction, and the scattering you would see would be from a structure represented in the the YZ plane. You can draw simple objects, such as a sphere. The matrix wave is simply named MAT, and a real radius of, say, 50 angstroms, and an X center, Y center, and Z center of 50, and a fill scattering length density value of 10, which would correspond 10 times 10 to the minus 7, or 1 times 10 to the minus 6 inverse angstrom squared. So you continue. It draws a sphere of that size in that location. If you wanted to, say, draw a cylinder along the z direction of a certain size and length with a different scattering length density of, say, 20, that can be drawn. And it looks like it hasn't shown up. It actually sort of looks like it knocked a hole in your sphere. In fact, what happened is the display is only showing values of 10. So if you, under the Gizmo menu, show info, and expand this a little bit, if you click on voxelgram, these are not pixels, these are actually volumes, so they're voxels, not pixels. Click on voxelgram, and then the value of 10, which was the sphere we drew, is blue. If we pick another color of 20 and say make that kind of a reddish color, and alpha is essentially the transparency, we can make that about 0.1, the pixels, the voxels become somewhat transparent. So now we have a complex object that is not really possible at all to describe with an analytic function. At this point, there's a multiple number of ways that we could use to calculate the scattered intensity. If we simply take the 3D Fourier transform of this and reduce it to 1D, it only takes a couple seconds, and we can plot the results. And this is the results of the calculation. What you can also do with the Fourier transform is get the 2D slice of what the detector plane would look like in this case. And you see a 1D representation of this. It's rather noisy in this case. But the 2D, you can see, has very fine fringes along the vertical, or in this case, in this representation, the z direction, because the length scale is very long. The fringes are a lot more wider spaced in the y direction, and you can also see the ring here due to the presence of the sphere there. So this is dependent on the orientation. If the structure had a different orientation, then the Fourier transform, what you would see in the YZ plane, would be different. You can change the orientation by either transposing the matrix or rotating the matrix. And if we transpose the matrix and then redo the Fourier transform, the one-dimensional Fourier result does not change, but in fact, if we get the two-dimensional slice, we see that is flipped 90 degrees as the structure was flipped 90 degrees. The other possibilities for the calculation are calculated as Debye spheres. This uses Debye's formula, the double sum. This is very slow. A binned Debye calculation, this is the method popularized by Otto Glatter, which bins the distances and is significantly faster. This method, unfortunately, can only handle a single scattering length density in the system. The Debye sphere method can calculate with any number of scattering length densities. Somewhere in between in speed is a binned scattering length density method. The name of who popularized this escapes me right now. It is actually in the help file. This method bins the distances, uses multiple scattering length densities, and is somewhat faster. The Fourier transform method makes use of all the different scattering length densities automatically. The differences between the Fourier transform method and any of the binned methods or the Debye methods are the Fourier transform inherently, through a choice of the number of cells and the length per cell, inherently sets the delta Q, Q min, and Q max. With the Debye sphere methods, you can choose exactly how many Q points you want. So for, say, the bin method, we can choose 100 Q points, the minimum Q, maximum Q. You click continue, and it's going to give you an estimate for the time of the calculation, which will in this case depend not on the size of the box, but on the number of spheres present. This should only take a few seconds. We'll say yes, and it's finished. We can plot the results, and it appends them to the same graph, and we can see both calculations do a very good job of calculating the structure.